Hello one and all. So now I'll be walking you through the assignment answers of part 1 for our assignment 3. So coming to the first question, it is like the elbow in VAEs and the diffusion model. So in variation autoencoders, we use the elbow, which is nothing but the evidence lower bound. So this is to approximate the interactable log likelihood. So this is written as the reconstruction term, and also we have a KL divergence term in this. So elbow is nothing but the expected log likelihood function of the data given in the latent variable minus the KL divergence between the approximate and the true posteriors. So this means the VAE tries to reconstruct the data while keeping the latent distribution close to a prior like a standard Gaussian. So in diffusion models, we don't use elbow directly. So, but we still minimize the sequence of KL divergence between forward and reverse noising steps. So this is similar to each step of the reverse denoising tries, which approximate the true backward process. So both frameworks aim to learn generative models that balance fidelity and structure using the variational principles. And coming to the second question, it is beta VAE is objective and latent representation. So a beta VAE changes the original VAE objective by adding a weight beta to the KL divergence term. So the new objective is to reconstruction loss minus the beta times scale divergence. So if the beta is greater than 1, we get more distanglement in the latent space, which means the different latent dimensions capture different data features like shape or color. But if the beta is too high, reconstruction quality suffers because the model prioritizes making the latent space too simple. And whereas if the lower beta focuses on better reconstructions, but may result in entanglement of the latent variables. So tuning beta gives us control over the trade-off between reconstruction quality and interpretable latent variables. And the third question is like theoretical part of the diffusion process. So in diffusion models like DDPNs, the forward process gradually adds Gaussian noise to the data over many steps until it becomes pure noise. The reverse process is learned by the model to denoise step by step. Theoretically, this is based on the Markov chains and score-based modeling. Each step is a Gaussian transition. So we model the reverse transitions using neural networks trained to predict the noise or the original image. So to generate the new samples, we start with random noise and run the learn reverse process. So essentially, the diffusion process allows us to learn a smooth probabilistic mapping from noise back to data. This results in very high quality image generation. And the fourth question is Gaussian VAE loss and the reparameterization trick. So the Gaussian VAE loss has two parts: the reconstruction error and the KL divergence. So we assume the latent variable z is sample from a Gaussian with learn mean and variance. So the KL divergence measures how different this is from the standard normal prior, and we can compute the part this part analytically also. So the reconstruction loss measures how well the decoder rebuilds the original input from the latent code. But since sampling is not highly differentiable or the non-differentiable, we use the reparameterization trick. So instead of sampling z directly, we sample e from standard normal and compute z equal to mu plus variance into e. So this makes the whole process differentiable. So we can just train the model using the gradient descent. And fifth question is like the papers, research papers we discussed in the class. So basically, we have discussed a lot of research papers, and some of them are the diffusion model, which is a comprehensive study of both networks and applications, denoising diffusion, probabilistic models, the deep generative image modeling using a Laplacian pyramid of adversarial networks, generative adversarial networks, improved techniques for training GANs, and conditional generative adversarial networks, and the hybrid normalization, which is towards the stable and efficient transformers training via hybrid normalization. And the last one is like auto encoding variational bytes. So these are the few papers which we discussed in the class. All of these papers highlight the diffusion models, GANs, VAEs, and the training and all. So we have learned a lot of knowledge from lot of knowledge about VAEs, GANs, and diffusion models from these papers. And the sixth question is like my reflections on the learnings from the class. So this semester I have learned how to build and understand generative models like GANs, VAEs, and diffusion models and transformers. So these models have revolutionized AI in these days. We have known this already. So these empower the tools like ChatGPT and all. By learning their math theory and implementation and the back-end process of all these models, I feel confident applying them to a real-world task like image generation and creative AI. So this will help me find an co-op or internship, or maybe I can use this knowledge back in my job after getting a full time and build my own projects. So personally, I am confident by learning these topics, and I feel I can explore more creative tools and AI-assisted design using these models. And now I have a proper foundation to do that. So this will be my reflection on this Spring 2025 learnings. So thank you.